Last time, we reformed a tubular leg and then sistered it with some angle iron. And we looked at a bending analysis of the original tube. And today, we're going to do the same thing with the sistered leg. So let's take a look. So remember, we had our frame subject to 50 pounds from the side with 84-inch legs. So the maximum bending moment in our legs was the 50 pounds times the 84 inches, or 4,200 inch-pounds. We can use the same equation for bending as before, sigma equals my over I, but our geometric parameters are going to be a little bit more complicated because we're looking at angle as opposed to tube. So we have m, but what about y? So let's look at our cross-section. Even though angle has radiused edges, we model the cross-section as two rectangles. We're using 2 by 2 by quarter-inch angle. If we were looking in a catalog for this material, this would be L2 by 2 by quarter-inch. So somewhere this cross-section has an area centroid, maybe somewhere around here. And when we apply a bending moment to this leg, it's going to want to bend about an axis that runs through its centroid. So then our maximum y value is the maximum distance away from this line, this axis, while still being within our cross-section. And so for the case of an angle, it's this distance away from the long exposed leg. This is our y value. So in order to get this y value, we need to know the location of this centroid. And the location of this centroid is denoted with y bar. And it can be found with this equation. This is the sum of all the areas of the various subshapes of your cross-section. I have two rectangles here, multiplied by the distance from some datum. Typically we pick the bottom of the cross-section to their respective centroids, divided by the sum of those same areas. So we've broken our angle, our compound shape, into two subshapes, two rectangles. And so each of these rectangles has their own little individual centroid. There's one for this left rectangle, and here's one for this right rectangle. So this left rectangle has an area of 2 inches by a quarter-inch. And this right rectangle has an area of 1 3/4 inches by a quarter-inch, because we don't include this last quarter-inch over here because we included it in the rectangle on the left. So let's just plug and chug and you'll see what I mean. So this is the area of the left rectangle multiplied by the distance from our datum to its centroid, and this is the area of our right-hand rectangle multiplied by the distance to its centroid, all divided by the sum of the areas. And we get that y bar equals 0.592 inches. And so to get y, we just take the 2 inches and subtract y bar. And we get 1.408. Let's move to a fresh page to find I. So I, the area moment of inertia, is our cross-sectional area's resistance to this bending moment. For simple shapes, you can look up I in a table that will be in the machinery's handbook or your reference guide for the PE or FE exam. But for compound shapes like this angle, or an I-beam or that kind of thing, you have to break it apart into subshapes, find the area moment of inertia for those subshapes, and then find their contribution to the area moment of inertia for the entire compound shape. So in this case, we have two rectangles. Here's our left-hand rectangle, and here's our right-hand rectangle. So each of these rectangles has their own little sub-area centroid. So we want to look at their moment of inertia about their own sub-centroid, and then use parallel axis theorem and find the equivalent moment of inertia about a parallel axis, an axis that goes through the centroid of the overall cross-section. So the equation for I then is the moment of inertia about each individual centroid plus the distance from the individual centroid to the overall centroid squared multiplied by the area of that subshape that we're analyzing, and then you add them all up. So for example, we can title this shape 1 and this shape 2. And we know that a rectangle has an area moment of inertia of 1/12 base 1 times height 1 cubed. So it will be the same thing for the other leg, 1/12 base 2 times height 2 cubed. Those are just the individual sub-shaped centroids added together, the I sub ci term for 1 and 2. But now we need to add our two d squared a terms. And for 1, d is this distance right here. The distance from our bending axis between the overall centroid and the sub-shaped centroid. And so we can see then that d sub 1 is the difference between, we could call it y sub 1, the distance to our centroid of our left-hand shape, and y bar from earlier. And b1h1, that's just the base and the height of member 1. We can do the same thing for 2. We have y2, which will just be the distance from our datum, the bottom of the shape, to the centroid of the right-hand rectangle, minus y bar again. These terms are squared, multiplied by the b2h2 area term. So plugging and chugging, we get 0.348 quartic inches, or inches to the fourth. And so that means that our normal stress due to bending in the angle is 16,993 psi. Assuming A36 steel from earlier, that makes our factor of safety 2.11, which is safe. Now, a couple comments. Really, our shape looks something like this after the legs are sistered. But because I had to reform this tube component that we analyzed in the other video, I want to be conservative, and I can't count on it taking any of the load, and so I'm looking only at the angle iron. You could do a compound shape analysis, and your cross-section would have a centroid maybe somewhere up here. And you would basically do the same analysis that we just did, but you would have to use another set of parallel axis theorem equations to figure out the contribution of the resistance to bending of the angle to the overall compound shape cross-section, and do the same thing with the tube. When you're designing something, time is limited, and it's good to be conservative. So just analyzing the angle in this case is totally sufficient. In fact, you could take it one step further, and oftentimes when I'm designing something with angle and I just want to do a quick check to make sure it's safe enough, I don't go through all of this parallel axis theorem analysis to figure out my moment of inertia. In practice, I just model it as the stiffer leg and look at the angle as if it's just a piece of rectangular flat bar, because I know that this floppy component, this floppy leg that's parallel with my bending axis, it's going to be contributing less to the resistance to bending than this rigid leg that's perpendicular to my bending axis. And I don't recommend shortcuts unless they're making your analysis more conservative. Shortcuts that make your analysis less conservative are cutting corners and not good. Let's take a real quick look at this. We know that this distance is 1/4 inch, and this is 2. The centroid is close enough to the center, so let's call it in the center, and we know that our moment is still the 4,200 inch-pounds times y over I. If we're looking at this simple rectangle, then y, the distance from our neutral axis, we can approximate as 1 inch, because that's the distance from the centroid of this rectangle to its outermost edge. I then, for a rectangle, is 1/12 base times height cubed, and the base is 1/4 inch, and the height is 2 inches. So y is an inch, I is 1/12 base times height cubed, and m is the 4,200 inch-pounds from earlier. We plug and chug, and we get 25,200 psi. And in our factor of safety equation, we get 1.43. And so you'll see, if I was just checking to see if this were safe enough, then I could bypass this analysis by virtue of doing this analysis, seeing that my factor of safety was greater than 1, and then knowing that the actual factor of safety is only going to be greater than that because my shortcut was a conservative measure that negated the floppy leg. So anyways, you got to do what works for your application. For getting an engineering degree, passing the FE or PE exam, you need to know how to analyze compound shapes using parallel axis theorem. But then in the field, for actual structures, this is often sufficient.